right, we're going to look at some practice problems now associated with controllability. So here we start off with the discrete time system, and we have, so here's our A, X, and B, U. We start with this initial condition. We want to go to this final desired final state. Okay, how did I pick that? Kind of randomly. But so according to the transfer problem, well, the solution to our difference equation has this: x at time 5, which we desire to be x of f, is given by a to the power 5 times the initial condition plus the control map times the control sequence. So this is our control map from 0 to 5. And so here it gives us these 5 control values. Okay, so this is what we have, and so these are unknowns right now. I don't know what the controls values are. I know the initial condition, I know the final condition, but I don't know these control values. But I do know all of this stuff, and so I know all of this, I know that, I know all of this. What I don't know is that. Okay. So our control control map is actually given by this matrix. We can compute the pseudo-inverse for this matrix here. Okay, and so again, because it's just a matrix, it's fairly straightforward to compute. And so now we can compute the minimum energy. The minimum energy is given by the pseudo-inverse times this stuff. And if we go through and multiply it out, we get this, which we can apply to our system. So this is what that sequence looks like. Okay, so we can do it. This is how we would do it. All right, so let's look at the control map now and how its range changes as we go through time. So B from 0 to 0 is just 0. Okay, so the range is 0. All right, so when B is 1, the control map is just the matrix B, which is just this, and it has this range. So if I multiply this by any scalar, that's basically in this range. So that's what we have. The control map from 0 to 2 is now given by this. So this is the control map. AB is this. And I can see that this matrix is non-singular, and so its range is all of R2. I can get the range of this is all of R2. If I continue going to 3, for example, I add this extra term to the matrix, so I get this. But this also has range, all of R2. And so we can see that the range of B from 0 to 1 is contained in the this should say the range of B, which is the range. So the range of this is contained in the range of that, which is equal to the range of this. Okay. So in this case, n is equal to 2. Looking at the Gramian now, so we take the control map times its adjoint, in which case we get this. The range of this matrix is basically the span of this, which is, again, the same thing that we got just looking at the control map. The control Gramian here is given by this expression. And so the range, in this case, this matrix we can go through and show has non-zero determinant. It's actually 2 minus 1, which is 1. So this has non-zero determinant, which means its range is all of R2. The Gramian up to 3 is given by this expression. We multiply it out, we get this. Okay, and so in this case, we can actually show that this matrix is greater than or equal to, in a semi-definite sense, than this matrix. And actually, yeah, actually it's greater than or equal to. This matrix here is greater than or equal to this matrix. Okay, and we can actually show that this matrix is strictly greater than that matrix. So sometimes we only get greater than or equal to, but since this one is greater than this one, which is greater than this one, it turns out this one is actually strictly greater than that one. And we can go through and show that. Now, in this particular example, the spectral radius of our A matrix is greater than 1. And so there is no solution to this infinite Gramian problem. Okay. However, there is a solution to this discrete time Lyapunov equation. We can go through and count it, compute it, and this is the k that we get. And we see that k is not positive definite. Okay. I have negative diagonal elements, So this shows us that our matrix is not positive definite. All right, so there's our Gramian for this problem. Because the system was unstable, we didn't get a positive definite Gramian. So notice that this equation I can solve because it's a linear matrix equality. That is, in the unknown k, this is just a linear equation. I can go through and solve for it by hand and find the actual values. And this is what I get. So even though I can get a solution to this equation, the solution is just not that infinite summation. That's the thing. It is a solution. It's just not a solution to that infinite equation. All right, here's our next example. So this one is stable. This A matrix is stable. Here is our Gramian up to time 1. Here's our Gramian up to time 2, Gramian up to time 3, Gramian up to time 4. And if I go all the way up to infinity, here's my Gramian. In this example, all of the Gramians happen to be diagonal. And that's because our system is in what's called controllable canonical form. Controllable. Controllable canonical. So canonical means it's a standard form. Controllable means it's controllable. And so for example, we can see this has full range. Therefore, it is controllable. So in this case, n is 2. So we go up to 2 steps, and we can see that this has full range. So I can go through and show that this matrix is less than or equal to this matrix. This matrix is less than or equal to that matrix, which is less than or equal to that matrix. This matrix is actually strictly greater than this matrix. And this matrix is strictly greater than this matrix. Okay. So I can see that by this process that as I go from 1 to infinity, my matrix, the inequalities keep nesting. Okay, so notice that this matrix is not strictly less than this matrix, because if I subtract the two, I'm going to have 1 and 0, which is not a positive definite matrix. Similarly, if I subtract these two matrices, I'm going to get 0 and 1/16, 0 and 1/16, but that 0 there is going to make it semi-definite, not positive definite. But if I subtract these two matrices, I'm going to get 1 and 1/16, and that will be a positive definite matrix. So this matrix is strictly greater than that matrix, and so forth. Now, in terms of modal aspects, suppose I have this system in discrete time, and I can show that I have this left eigenvalue and eigenvector relationship. So lambda is equal to -3, w is given by this vector. I can go through and show that if I multiply this times this matrix, I will get -3 times this vector. And I can also show that if I take this vector and multiply by this matrix, this B matrix, I will get 0 and 0. So this is an example where I have a left eigenvector that proves that my system is not controllable. Now, for that same system, I actually have this eigenvector matrix, and so here are the eigenvalues, -1, -2, -3. And so when I actually go through and, so this is in the new coordinates, if I use now modal coordinates, that is, if I use as a transformation matrix my V, actually the inverse of V, this is what I get. And so notice that this row of zeros is associated with that eigenvalue, and so we have an uncontrollable mode. So an uncontrollable mode is associated with a row of zeros in the B matrix in the transformed coordinates. Okay, so it's associated with a row of zeros. So that is an uncontrollable mode. If I now looked at this quantity, this xz, I can go through and show that it's equal to this. If I plug in 3 for -z, this is the matrix I get. I can go through and show for that same w, I can multiply it out and show that I get all zeros all the way across. So even though it looks like these guys, it's hard to, I mean, these guys are obviously linearly dependent, but like this is not linearly dependent on that. But all of these vectors multiplying by that w gives 0. So this again shows that we have that uncontrollable mode. Now for continuous time systems, I have this system, and I want to go from some initial condition to some final condition at time t equals 2. Okay, So I want to go through the transfer problem. How can I do it? How can I do it? Okay, so here's our system. And so we basically need to satisfy this equation. That is, our control signal needs to satisfy this equation. And so if you recall, the control map actually is this convolution operator, but we don't know what u is. So unlike the discrete time problem where we could kind of extract u and just work with b itself, here we can't do that because u is fundamentally a part of our control map. So we need to know what u is in order to be able to perform this integral. So, but if you recall, the control map maps signals in this space into all of our n, and the adjoint maps backwards, and also the pseudo-inverse maps backwards. And so we saw that we had the adjoint, and the adjoint can be written this way. Okay. So for some vector v, we have this. And now we set v equal to all the stuff that we need in order to go from state x at 0 to state x at f. Okay, so using MATLAB, I can actually go through and compute all of this. Okay, e to the at, I can compute. xf is given to us, x0 is given to us, and so I can actually go through and compute it, and this is what I get, which is approximately given by this. Okay, and so I can actually get a numerical value for the vector v that I need. In terms of my Gramian, I recall that I have b times b adjoint times v, but we could also work with k directly in terms of the state transition matrix and b. In our case, our b is time invariant, and so it's also real. So all of this stuff just becomes bb transposed, and then I have the state transition matrix. So t and tau is actually t minus tau, but we're going to 2 as our value of t. And so this is just an expression in terms of tau, and once we integrate with respect to tau, we just get a numeric matrix, and so this is our numeric matrix. Okay, and so we can go through and show this is what we get when we actually perform that integration. Kind of a messy integration, but actually you can do it using the symbolic math toolbox, no sweat. Notice that this matrix is actually symmetric, which we would expect it to be, but we can go through and show that this matrix is singular. That is, it's not positive definite, it's positive semi-definite. And because it's not positive definite, we cannot solve the transfer problem because we need all of Rn to be the range of k. So we're kind of stuck with that. Well, we'll look at a different example. Here's another system. Here's my initial condition. I want to go to this final condition. So again, I can compute my v, which is xf minus e to the at, the t final, which is 2, times the initial condition. And so I get this expression, which numerically gives approximately that. So MATLAB gives, you can use the rat function to get rational approximations of things, and those rational approximations are much simpler than writing out all 16 digits of the decimal value. If I compute now the Gramian from 0 to 2, that's the integral from 0 to 2 of all of this stuff. So I can again do this in the symbolic math toolbox, and so this is what I get. Okay, and so here's my controllability Gramian. And so if I now take the pseudo-inverse operating on v, where the v is the v that I am going to be using, right? The v that appears in my formula. So I'm going to take all of this quantity. Between 0 and 2, I'm going to use this expression, and 0 otherwise. So I can actually plug all this stuff in and get this expression in terms of tau, as a function of tau. So I actually get this expression, and again, it's just by by computing this. So as complicated as this looks, as hairy as this looks, I can simplify it down to all of this, which is not very complicated. I can even plot it. So here's the plot of that function. So this is the control signal from time 0 to 2, and it's given by the pseudo-inverse operating on the vector v, where the vector v takes into account the initial state, the final state. So if you're wondering how to compute all of this stuff, here is how you would compute all of that stuff. So I use the symbolic math toolbox. I define these variables. I take e to the at, and here's v. So as complicated as it looked like to compute, it's not actually that complicated. To actually get numerical values, I can actually substitute the final value t in for 2 in for t, and then I can go through and compute my Gramian. So this is like the stuff that goes inside the integral. I integrate it from 0 to t. If I evaluate that at 2, I get this. This is now going to be a numeric matrix, and now I can compute all of this quantity. Okay, and this is a numeric quantity, and that's the quantity that I showed. So BP here is the pseudo-inverse of B operating on the vector V. So that's what we get. So this is actually gives us our control sequence, and it'll give it as a function of time tau. Here TT is, instead of using tau, I'm using the TT. And so it gives us the actual function. And that's actually what we're plotting here. Okay. We just plot this versus tau. Okay. So if I apply that to my system now, then I can show that I actually go from initial state, here was the initial state, 1 and minus 1, 1 and minus 1, and I go to the final state, 1 and 0, 1 and 0. Okay, so my control signal actually it pushes the differential equation so that it starts at this initial state, ends up at that final state. Okay, and it does some stuff in between, which you would expect. It doesn't just jump from here to there. It goes along some path. But it takes the path, and actually the path it takes is what's called the minimum energy, minimum control energy. We use the pseudo-inverse of the control map in order to obtain this. And so in the process of using the pseudo-inverse, we've actually solved a least squares problem, which is really a minimum energy problem. So this is the approach taken when we use minimum energy to go from this state to this state. And so we started off with some initial state, some final state. I could have chosen started from a different place and ended up in a different place, and where that would have come in was the v vector, and so I can actually change either of these two values and get a different control value, and as a result a different path that I go through. So this shows the controllability problem, the transfer problem, the Gramian, and also we've looked at some modal properties.